So, let us take some arbitrary vector in a vector space capital V and ask this following question. Can we obtain at least one subspace of capital V which contains this particular vector? So, let's look at it with an example. So, let V be equal to say 1 1 0 be an element in R3, be a vector in R3. So, let us ask this question: can we obtain subspaces, at least one subspace of R3 which contains V? So, clearly R3 itself is an example, right? R3 is a subspace of R3 which contains V, but that is boring. We would like to look at something which is a proper subspace, which is smaller than R3. Certainly, the 0 vector space will not do, because that is too small, that contains only the 0 element, it does not contain V. We would like to look for subspaces which will contain V, but which need not be the entire space. We might not be able to actually do that, but let us see if we can do that in this case. Might happen that the only subspaces which contain a few given vectors is the entire space. That can happen, but let us see. Let us focus on just this vector V100 which is in R3 and ask that question. So, suppose our W is the set given by the singleton V. Let us see, is this a subspace? Okay, good question. Is this a subspace? I would say that a few minutes of observation will tell you that it is not closed under vector addition or scalar multiplication. It is just certainly a subset of R3, but it is certainly not closed under vector addition and scalar multiplication, because what is 2 times V plus V is just equal to 2 comma 2 comma 0, right? V is 1 1 0, so V plus V, which does not belong to our W, because W is just containing 1 1 0. Similarly, you take any scalar multiple of V for that matter. Let us look at pi times 1 1 0. Notice that I took pi purposely because we were only considering 2 times, 3 times and all that. 2 times the vector, 3 times the vector and such examples. Any real number should work as a scalar. That is the reason why I have taken pi. This is just going to be equal to pi comma 0. And that certainly does not belong to our W. So, the singleton W is not a vector subspace of R3. Okay. One thing which we will immediately notice is that if there is a vector subspace of R3 which contains capital W, every scalar multiple should certainly be there, right. So, let U be the set of all A times V, where A is in R, all real numbers, or A is in F, whichever you want to call it. Then notice every subspace of R3 which contains V should certainly contain U, because a subspace is closed under scalar multiplication in particular. But then my claim is that U itself is a subspace. So, let me leave it as an exercise for you to check that U is a subspace of R3. So, not only have we obtained a subspace of R3 which contains our vector V, we have also checked that any subspace of R3 which contains the vector V should also contain this. So, in some sense it is the smallest subspace which contains our vector V. Okay, let us play the game with more vectors now. So, let V be equal to 1 1 0 and W be equal to, small w be equal to 1 0 3, and let us ask the same question: what is the smallest subspace or let's not ask smallest or anything, let's ask, can we get hold of one subspace which contains V and W, which might be, which could be a proper subspace and not the entire R3 itself, or which is a proper subspace of R3. Might and could will not fit there anyway. So, like in the previous case, the first thing to notice is that if V is there, any scalar multiple of V should also be there. So, notice that every scalar multiple of V should be in any subspace that contains V. Similarly, any scalar multiple of W should also be there. Should be in, just writing it again, which is inefficient, but let me do it anyway. In any subspace that contains W. So, in particular, A times V and B times W, where A runs over all scalars and B runs over all scalars, will be in W if W contains V and W. But are they all the elements they will contain? We know more. Then AV plus BW also belongs to W, because W is a subspace, right? And subspaces by definition should be closed under vector addition as well. So, we know that for any scalar A, AV belongs to W, and for any scalar B, BW also belongs to, B small w also belongs to capital W. But then these two are elements in capital W, their sum, the vector addition of these two should also give you an element which is in capital W, and that is why AV plus BW also should be in capital W. So, let us do one thing, let U be the set of all AV plus BW such that A is ranging over all scalars, B is also ranging over all scalars. Then we just noticed, then U is contained in W. But then again I leave it as an exercise for you to check that U itself is a subspace. And therefore, so it is in some sense the smallest subspace which contains V and W. So, elements of this type AV plus BW is what is called as a linear combination of V and W, and the collection of all such linear combinations, in this case which is denoted by U, is what is called as the span of V and W. So, let us give a formal definition of a linear combination and a span. So, let me just note it down here anyway. The elements, the vectors of the type AV plus BW, where A and B are scalars, are called linear combinations of V and W, and the subspace U is called the span of V and W. Of course, this was for a very special case, right? We took two vectors v and w in R3, and then we were discussing all these things. So, let us now give a formal definition of what is meant by a linear combination and what is meant by the span. So, let S be a subset of V where V is a vector space. So, I am giving the definition of a linear combination and span. So, let S be a subset of V where V is a vector space. A linear combination in S is an element of the type. So, notice the language that is being used. A linear combination in S is an element, is a vector. Let me not use the word, let me use the word vector to denote that it is an element of capital V, is a vector of the type A1 V1 plus A2 V2 plus dot 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 AN Vn, where AIs are fixed scalars I equal to 1 to up to n are scalars, and Vi belongs to S, where again I is equal to 1 to n. So, let us revisit our definition. Let S be any subset of our vector space V, and you pick V1, V2 up to Vn arbitrary vectors in S and fixed scalars A1, A2 up to An. Look at A1 V1 plus A2 V2 up to An Vn. Such an element, such a vector is called a linear combination in S. So, if you come up to this example, 2 times W plus 3 times 2 times V plus 3 times W, where is the vector? Here it is. 2 times V plus 3 times W is an example of a linear combination of V and W, or pi times V plus E times W is a linear combination of V and W. Alright. Now, the set of all linear combinations is called the span of S. And is denoted, it's called span of S, and that is what it's denoted as. It's called the span of S and is denoted as span of S. So, formally span of S is the, by definition, is the set of all A1 V1 plus AN Vn, where AIs are scalars and VIs belong to S. So, the first thing to note here is that our n is not fixed here. So, in particular 1 times V1 equal to V1 belongs to span of S. V1 plus V2 belongs to span of S. We have not put any restriction on the AIs. The scalars AIs could be anything. It could be anything in the sense any scalar, any real number. It could be 0. It could be a negative rational number. It could be a negative real number, which is not a rational number, an irrational number. It could happen. So, we take any real number, look at combination with those, any color set of real numbers, and look at a linear combination with those real numbers, that will be the span of S. Notice that we have not put any restriction on the set S. If you go back to our definition, we have just taken S to be some subset of V, and we have defined the span and the linear combination in S, right? So, the span of S and linear combination in S and span of S. So, we have not demanded that S be finite or anything, S could be finite. However, the linear combination will always be of finitely many elements in the set S. If S is finite, then we could always consider the set span of S. So, let me just note it. If S is finite, i.e. S is equal to say V1 to Vn, then I could say that span of S is the this is already defined, this is equal to the set of all A1 V1 plus, in fact let me use a different n to denote that it is fixed, A1 V1 plus A2 V2 plus up to AM Vm, where AI's are any set of scalars. So, if S is finite, then the span will consist of linear combinations of all the vectors in S. But that is not saying much. I will just leave it as an exercise for you to check that the definition has not changed. Check that the definition, so maybe I can put this thing here, definitions match. So, what is there to check at all is the question, right? Here all varying lengths where n could be 1, n could be 2 and so on are being considered when we defined span of S in the formal definition a couple of minutes back. We had no restriction on considering all elements, of course we can't, we are only talking about finitely many sums. Here however, if S is finite, we are looking at the linear combination involving each and every element of S, that is the difference, and it is an exercise to check that it makes no difference. Alright, so let me introduce a convention here. Span of the empty set. So, in particular empty set is a subset of V. So, we could ask what is the span of the empty set. By convention, this is the 0 subspace. So, this is taken as a convention or an axiom, and let us now prove some results about the span. We have already seen glimpses of what to expect. Let me put it down as a theorem. So, let S contained in V, where V is a vector space, then span of S is a subspace of V which contains S. Moreover, if W is any other subspace which contains S, then span of S is contained in W. Span of S is contained in any subspace of V which contains S. Okay, let us have a look at the proof. So, we will try to keep the proof as rigorous as possible because this is amongst the first few theorems we are proving. Okay, so what are we expected to prove here? S contained in V is a subset of V which is a vector space. We would like to first show that span of S is a subspace of V. So, first note that span of S is contained in V since every element of span of S is of the type is given by A1 V1 plus up to AN Vn, where AI's are in capital S, I am sorry, AI's are in capital R and VI's are in capital S. But then since V is closed under both vector addition and scalar multiplication, under scalar multiplication, AI times Vi belongs to V, and closed under vector addition gives that A1 V1 plus up to An Vn is in capital V. So, yes, span of S is certainly contained in capital V. So, that was the first condition for something to be a subspace. W is a subspace of V if W is contained in V, and two more conditions are to be satisfied. The set W is closed under vector addition and scalar multiplication. So, in this case we would like to show that span of S is closed under vector addition and scalar multiplication. Let us first check closed under vector addition. So, let A1 V1 plus AM VM comma B1 V1 plus okay, so let me write down a statement and let me then justify that. An Vn plus up to Bn Vn be in span of S. Then A1 V1 plus up to An Vn, this plus B1 V1 plus up to Bn Vn is equal to, after all the properties 1 to 8, many of the properties will be used extensively. You should sit and see which are the properties which are being used. We will get this is equal to A1 plus B1 times V1 plus dot 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 An plus Vn times Vn, which belongs to span of S. So, if you take two vectors which are the span of the same vectors V1, V2 up to Vn, then the vector addition of these two put you back in the span of S. But if my point is that we are done with the checking of closeness under vector addition, because suppose you take two linear combinations of linear combinations in S, then suppose the V1 to Vn and W1 to Wn are the two different linear combinations. You look at the union and then extend the existing linear combination by adding zeros as coefficients of the ones which are not there, and then you can write any linear combination as the linear combination of the starting set with a few more elements with 0 as the coefficients, and therefore the two different vectors can be written down as the linear combination of the same vectors, and by what we have just checked, they are going to be in the sum of them is going to be in the span of S. We have checked that this is closed under vector addition. Just write down whatever I just said for the sake of completeness. So, let A1 V1 plus up to An Vn and B1 W1 plus up to Bm Wm be vectors in span of S. Then express each of these vectors as a linear combination of V1 to Vn or M, V1 to Vn and W1 to Wm, Vn and W1 to Wm by, maybe that is a bad idea to write it like this, let me put it this way, union W1 to Wm by with 0 as the coefficient, of vectors which were not present to begin with. Then let us now invoke what we have just noted, as the sum of two such vectors can again be written as a linear combination of v1 v2 up to vn union w1 w2 up to wn, which is an element of span of S. Then by using the above observation, let me put this as star. So this, let me call it as star. Observation star, span of S is closed under vector addition. The span of S being closed under scalar multiplication is far more straightforward. So let C be some scalar, let it be a real number, and let a1 v1 plus up to say an vn be an element in the span of S. Then C times a1 v1 plus up to an vn. What is this? This is a scalar multiplied to a vector, and by the various properties of the operations in a vector space which were listed in the definition, we have this is equal to C1 v1 plus up to C a n vn. But notice that C times a1 is just another scalar. Similarly, C times a2 is just another scalar. C times an is also just another scalar. So this again is an element in the span of S. After all, span of S contains all the linear combinations. This is also in particular another linear combination, right? So this gives that span of S is a subspace. We are only partially done. We would like to now show that S is contained in the span of S, but that we have already observed, right? S is clearly contained in the span of S. So let us prove it and then write it. Let V be some element in capital S. Then 1 times V is a linear combination in S. By the very definition. But 1 times V is just V. V is the multiplicative identity. So this gives 1 times V is in span of S. But 1 times V is equal to V, which implies V belongs to span of S. So every element in S is in span of S. This implies S is contained in the span of S. So we have shown one statement in the theorem. Let me recall what the theorem is. Let S be a subset of V where V is a vector space, span of S is a subspace of V which contains S. All that is left to show is that W, if W is a subspace of V which contains S, then span of S is contained in V. So let W be a subspace of V which contains S. We would like to show that span of S is contained in V. So let us take some arbitrary element in the span of S. So let a1 v1 plus, let me use a different term index so that n gives a feeling that it is always n. So let this be in the span of S. We would like to show that this element is in W as well. But notice that V1, V2 up to Vk, which are all elements in S, belong to capital W, and W is a subspace. W is a subspace, and therefore all scalar multiples of this also belongs to capital W. This implies that A, let me write it as A1 V1 belongs to capital W, A2 V2 belongs to capital W, and so on. An or Ak Vk also belongs to capital W, because all scalar multiples belong. But again, W is a subspace implies that it's closed under vector addition as well, and A1 V1 plus A2 V2 plus AK Vk is belonging to capital W. Therefore, span of S is contained in, because we took some arbitrary vector in span of S and we showed that that has to be necessarily in W. So, this means that this is contained in W, and that is precisely what we had set out to prove. So, next let us look at the notion of a spanning set. So, we say that a set spans the vector space V if the span of S is equal to V. So, we say that a set, a subset S contained in V spans the vector space V if span of S is equal to V. Notice that span of S is certainly a subspace of V, as we have just proved. We say that it spans the vector space V if the span is the entire vector space. S is called a spanning set of S. Then S is called a spanning set of S, spanning set of V. This is the definition of a spanning set. So, what is a spanning set? You take some subset S of V, check whether the span of S is the entire vector space. If it is the entire vector space, then we say that S is a spanning set of V, or that S spans V. Let us look at some examples. So, the first example would be to consider, say, R3. Let V be equal to R3 and S be equal to the set 1 0 0, 0 1 0 and 0 0 1. Then you consider any x comma y comma z. This can be written, I will just write down explicitly what the linear combination of the above elements or above vectors are, which will give us x y z. This is going to be x times 1 0 0, notice that x is a scalar, plus y times 0 1 0 plus z times 0 0 1. And therefore, any x y z can be written as an element in the span of S, which means that V is contained in the span of S. Hence, S is a spanning set of capital V. Spanning sets are quite remarkable, right? R3 contains infinitely many elements, but we just showed that any element of R3 could be written down as a linear combination of these three elements. Right. Next example. Let us look at V to be equal to, say, R2 and consider S to be equal to 1 2 2 3 3 4. I would like to show that 1 2 and 2 3, if you look at any element x comma y, suppose this is equal to a times 1 2 plus b times 2 3. Just let us focus on 1 2 and 2 3 and let us see what we can do. Can we get hold of some a and b such that this happens? Well, this just tells us that x is equal to a plus 2b and y is equal to 2a plus 3b, and this tells us that y minus 2 times x is equal to, or minus of this is equal to B. And similarly, we can get hold of A, calculate A, I will leave it to you. And we have just shown that given any xy, we will be able to write xy as a linear combination of 1, 2 and 2, 3. In particular, if you look at S, which has 1, 2, 2, 3 and 3, 4, you can write any element as a linear combination of S, or any element as an element in the linear combination in the span of S. So, this implies that S is a spanning set. Again, but if you just look at this example, you will notice that the 3, 4 was not needed, right? 3, 4 was lying there as an unnecessary wastage. We could have written any element in R2 as a linear combination of just 1, 2 and 2, 3. So, the junk vector 3, 4 is in some sense dependent on 1, 2 and 2, 3, and that will be the content of the next week. That is how we will begin the next week, by discussing what is called as linear dependence and independence. So, let me stop here.